I think my best work has been coming up with new experiments to test fundamental physics. I've come up with new ways to test the theory of the speed of light. I've come up with new ways for quantum gravity tests, and now I'm coming up with new ways to search for dark matter. Precision measurement underpins everything we do in measurement technology, from measuring time, trying to measure a signal on radar, trying to detect a gravity wave. Every one of these measurements has noise in it. The noise limits your ability to detect these things. So if we want to detect that signal, it's just a matter of improving our signal-to-noise ratios. I started my PhD on the resonant bar detector. The interesting thing about that detector is it's what's known as an optomechanical system. And optomechanical systems are now fundamental in quantum measurement. And we actually did some groundbreaking work before the new discipline existed. For example, when you have this acoustic resonance interacting with this photonic resonance, you can cool devices. And we did the first ever resolved sideband cooling of a mechanical oscillator. So we had to develop this precision technology, and that led to this Sapphire Clock project. And we started supplying the Sapphire Clock around the world. It was supplied to the French Space Agency, supplied to Paris Observatory for their time network, and we also supplied one to Berlin for a combined test testing the speed of light, which is the current best test. There was a company in Fremantle that licensed the technology, and eventually they were brought out by Raytheon and is now in all of Raytheon's radar. And we're still building those devices and we're still using them. In fact, we're making a more high frequency device, which is in the 5G bands, and we're making it tunable. The thing about 5G, it's different to the 3 and 4G. The property of the oscillator is one of the most important parts. We also use these cryogenic versions of the technology, where we now go down to millikelvin in temperature. And to get there, you need a millikelvin refrigerator called a dilution refrigerator, and it's capable with a big magnet to turn dark matter into photons. And as soon as we turn that dark matter into photons, we've now got our same signal-to-noise ratio problem. So we have to use this technology that we've developed over the years to try and read that out. And we've been successful in that and we've got a whole bunch of new ideas. Cryogenic versions of these devices, even though in principle they can operate better, many companies don't want to deal with such sort of complicated equipment. So we developed these very portable low noise oscillators. For example, the gravity gradiometer with Lockheed Martin uses this technology, creating a readout with this optomechanic system. So we'll have this acoustic system, and if it passes across a gravity gradient, it will distort. So if you put it down a borehole, you can detect minerals. And if you can put it on the drone, you can use it for defense purposes to see if you can find tunnels, and you might be able to even use it for navigation. To do this sort of work, to build these precision technologies, it opens up many possibilities to improve precision of current measurements.